Okay, so welcome everyone to the next QFT in Geometry seminar. So just in terms of format for the seminar, if you have a question, unmute yourself and just shout it out if you like, or you can type it in chat to everyone, and then the organizers can relay it to the speaker. And please keep yourself muted so that there's not a lot of background noise. If you're interested in being on the mailing list, just contact one of the organizers, either through chat or email, and we'll see what we can do about getting you on the list. I think that's it for organizational stuff. So now we're very happy to have Cumrun Vafa from Harvard University, who's going to tell us about Cobordism classes, baby universes, and the Swampland. So,
okay.
Please.
Thank you. Thanks for inviting me to give a talk in this series. This is my first talk via Zoom, so I would be happy to see how it goes. So let me share my screen. Let's see if that works. I'm assuming you see my screen. Yes. So I'm going to be talking about basically two papers, both of them with my student Jake McNamara, and one is pre-COVID and one is post-COVID. So that's one of them is fall and one of them is a past month. So let me go here. Let's see, how do I advance this? Okay, so so this is roughly the organization of what I have. It's going too fast here. So we have, so let me just go back to the first page. The pages are advancing at a different rate. So anyhow, there are 7 basic topics I'm going to do. First, I'm going to introduce what I'm the basic structure of the talk, what I'm aiming for. And roughly speaking, the talk is going to have 2 components. The topics from 2 to 5 is basically the ideas related to Cobordism. And the last 2 topics are related to baby universes. So in the context of string theory, we have come to believe that there is a uniqueness to quantum gravity, and the way we understand this is in terms of a duality web. We know that you can go from any string compactification to any other. Sometimes you have to decompactify or recompactify to go from one string theory to another, but basically we believe that there is a unique quantum gravity at the end of the day. Of course, we don't have a proof of this statement, but it's strongly ingrained with us, and given all the experience we have, it seems to be quite a robust expectation. However, this uniqueness of quantum gravity is uniqueness via a infinite distance in space. In other words, you have to sometimes decompactify and recompactify and so forth. So even though there's a unique quantum gravity in the sense of connectivity, but they're at infinite distance from one another. And one can ask whether or not this connectivity is actually stronger than that, whether 2 theories can be strongly connected to different quantum gravities even before compactifications. For example, we know type 2A and type 2B are the same theory once you compactify them on a circle by T-duality, but so in 9 dimension there's no difference between them, but in 10 dimension there is a difference. Type 2A is non-chiral, type 2B is chiral. They are not dual to each other in any sense in 10 dimension. But could there be a domain wall, let's say, which you can go from one side to the other and go from type 2A to type 2B? So as we will argue, based on ideas from the Swampland, which tries to differentiate quantum field theories which can or cannot arise in the low energy limit of quantum gravity, that suggests the answer to this is yes, that we indeed should be able to go from any quantum gravity to any other in the sense of going through a domain wall. And this will have consequences in particular for baby universes and ensemble interpretation for holography, or in fact, the lack thereof, that whether or not we can have ensemble interpretation for holography. So let me start with the definition of what do I mean by Cobordism classes. So if I have 2 manifolds, M and N, which is K, let's say they're both of the same dimension, K, we want to say that if they are cobordant, if you can have a process in which you can go from one side to the other, ending up from one manifold to another. So in other words, in this context, these 2 manifolds M and N, we would call them cobordant. So there's a k plus 1 dimensional manifold whose boundaries are n minus m. In this case, we say m is cobordism to n. From the viewpoint of string compactification, this would look like you're compactifying a string theory on a manifold M. So you'll end up with some theory here. And you can think about this direction as a direction in macroscopic space. And so you can think about you're going from one place to another in the macroscopic direction, and something happens in the middle, like these holes here. This is what we would mean by domain wall. And when you emerge on the other side, you're getting back again to the manifold, a different manifold, this case manifold n. So you would say that the string compactification of one type is related to the other one through a domain wall. In fact, Cobordism defines an abelian group by defining addition. So you say you take two manifolds M1 and M2, and you define an addition of Cobordism if there is a manifold one higher dimension whose boundary is n minus M1 minus M2. In other words, M1 and M2 can go from left to right. From the viewpoint of string theory compactification, this situation on the left would look like having two copies of the macroscopic space, one corresponding compactification on M1 and the other one M2, and they are joined by a domain wall, or on the right, they go to a different manifold N. So this defines an addition law for Cobordism. And in fact, one can also define the element 0. The element 0 in Cobordism is defined by asking whether a manifold can be a boundary of a compact one higher dimensional manifold. In other words, it's cobordism to nothing. There's nothing on the right side. So this is the 0 element. Again, if you view this from compactification perspective, you have a compactification to some macroscopic space here on M. And if you move to the right, you find that it stops. So therefore, you have a boundary so this would say that the quantum gravity will have a boundary, can admit a boundary where the space stops. So in the context of Cobordism, in the context of string theory, we can view Cobordism as defining classes of compactifications which can be deformed from one to another by finite action processes. In other words, you are going from one part to the other with an action which is not infinite, and so there's a finite process. And if we can do this, we would say that there's a stronger equivalence because we are not going through infinite distance, which would require infinite action if you go from one to the other. To be more precise, when we define the suitable Cobordism in D dimension, if you want to restrict your attention to capital D here denoting macroscopic dimensions, if you want to define what you mean by quantum gravity in D dimension, we just say we have a space that have a consistent quantum gravity in the D-dimensional space-time, macroscopic, let's say. So locally, it's like RD. And we want to see what do we call equivalent in this language, because you can have different string theories. So if you take a particular string theory of dimension small d, then the corresponding compactifications will be characterized by Cobordism classes, omega k with some structure, and that structure will depend on the manifold. The star here denotes the restrictions that you need to put on the category of manifolds which lead to consistent compactification for a given specified string theory. What that category is, what that star is, will of course be different. So indeed, so I'm here thinking about this Cobordism class of quantum gravity in a broader sense than a mathematician would define it. Here I'm defining not with a specific definition of a manifold, but with more generally possibility of having different manifolds of different dimensions if you have a different string theories, which you are having on the left and the right. For example, you could have M theory on a compactified on T2 being type 2B equivalent to an S1. And so you have on the left and the right, you will have two different objects which look rather different in that language. So we are not necessarily restricting the particular geometry of the manifold, but for a given corner of the string, weak coupling string, we will have a specific meaning to think about this omega d of qg with respect to the Cobordism of an internal manifold with some structure determined by the string theory that we are interested in. And in this case, the k will be the internal dimensions, which if you're having a string theory in d dimension, that difference would be d minus the capital D. So the conjecture that we want to propose is that in a quantum theory of gravity, all cobordism classes are trivial. The main motivation comes from this uniqueness hypothesis, and it implies that any two quantum theories of gravity in d dimensions can be connected by a finite tension domain wall. So it's a strong sense of connectivity. And it's also related to the intuition that there are no global charges in quantum gravity. That is, if you have a cobordism class, you can think about using that to define a charge. And therefore, if you cannot go from one charge class to another, which you cannot if you have a distinct cobordism class, then you will have a global charge, and that should not be possible in the quantum theory of gravity. So motivation comes from basically an extension of what we mean by lack of global symmetries in the quantum theory of gravity. Now, all theories compactified to d dimensions would be connected in a given dimension if omega d of quantum gravity is 0. Now, this would mean that all compactifications for a given string theory should be cobordant to nothing. So if you fix a particular string theory to try to get capital D macroscopic dimensions by suitably choosing a compactification M, then all such M's should somehow be related to a situation where you have nothing on that side. So you will have to have a cobordant. So every manifold should be cobordant to nothing means that you will be able to have a situation like this no matter what compactification you start with. This means that for a quantum theory of gravity to have a non-trivial cobordism, you'll always have to have a boundary. In other words, your space-time should admit a boundary. So you can think about it, in this case, domain wall to nothing, or just the boundary of the space-time. So this would be basically equivalent to the statement of triviality of cobordism. Namely, the conjecture would be that any quantum gravity in any macroscopic dimension should admit a boundary. And of course, you can bring two boundaries together if you have two different string compactification, and you can merge them together to form a domain wall going from one theory to another. So in this way, you can combine two different quantum theories to each other, go from one to the other through this process by attaching both of them to nothing, so to speak. So in this way, the basic statement can be summarized by saying, in a physical way, the expectation would be that any quantum gravity will need to admit a boundary. So let me define the simplest example of this, which comes from string theory, which illustrates the point of it. So let me consider P-form gauge fields, like the one we have in string theory, M theory, or whatnot. And these define cobordism classes. So for example, you can consider a manifold which has a cycle. Here I denote the cycle by M, for which the integral of F over it is not 0. So this defines a class for the cobordism. And the conservation law in this case, the cobordism class that we are defining, follows from the conservation that D of F is 0. So this defines a non-trivial cobordism classes, but this would be inconsistent with the conjecture we are making. So what is the story? Well, the story is that D of F is not exactly 0. In other words, we can have defects or sources for F. So if you start with a flux through M, you can undo the flux, so to speak, by having a defect which carries the corresponding charge, in this case a magnetic charge, which gives rise to that flux. So in other words, if we did not know that the spectrum of the theory is complete, F would have defined the non-trivial cobordism class, but the triviality of the cobordism class in this case predicts that there must be a defect. In other words, the spectrum is complete. You can, for every class of charge you put here, there must be something which kills it. And that is a rephrasing of what, of course, is one of the basic known principles of the Swampland, which is that the spectrum of any gauge theory, any gauge field is complete, which is, of course, itself is related to the lack of global symmetries. So this is an illustrative example, and this also shows that to say that cobordism is trivial is not a trivial statement. In other words, it bites, it has predictions. It tells you have something, you have a complete spectrum or something. So this vanishing might sound like it's a boring statement, but actually is a quite powerful statement. It's somewhat like in quantum field theories, we're familiar with anomalies. So if the anomalies, we say the anomaly should be 0 for a gauge theory, let's say, gauge anomaly should be 0 is not a trivial statement. It is, if you have a theory which has some, you have described some spectrum in your theory which does not satisfy the gauge anomaly vanishing, then you can predict there must be other things in your theory to cancel it. So that kind of thing is similar to what we are using it here. The vanishing of the requirement of vanishing of cobordism is a non-trivial statement and makes predictions like there are defects. So in defining the cobordism classes for compactification of string theory, we have to know what conditions we put on the class of manifolds under considerations. All superstrings involve spinors, so the structure should include spin structures. So some string theories like type 2b require orientable manifolds, whereas some others like type 2a and M theory allow non-orientable ones. So that structure star includes in particular the spin structure, but it might include other things like flux allowed, this and that. So there could be many other possible things that we should put as what do we mean by star. For me, for us, let's just start with the bare bones. Let's ignore all the fluxes, turn everything off. We just consider compactifications on a manifold. And so the bare bones of the star structure would be that we have to allow a manifold with a spin structure. And if it's orientable, like in the case of type 2b, we have a spin cobordism classes denoted by omega k. And for the cases like 2a or M theory, which you may have non-orientable ones, you have to allow for pin plus cobordism classes, which are somewhat different. So let us first consider the case for type 2b. And in this case, we need to consider spin manifolds. And the cobordism of spin manifolds in various dimensions are written here up to dimension 7. So these are the cobordism classes. And as you can see, they are non-trivial, contrary to what we were hoping or expecting in this case. So what happened? Well, what happens is that exactly like what happened in the case of the gauge field, F that we were talking about, there are classes, if you ignore something, and if you remember that there are extra ingredients, by adding those bells and whistles, you get rid of that class. So let's see so we are hoping, therefore, that some of these can be gotten rid of in some way, one way or another. So for example, let's look at k equals to 1 in dimension 1, compactification on a circle of type 2b. So we want to have a circle to be trivialized as a boundary of something. Now, a periodic circle is not a boundary of something. That's by definition for a spin manifold, it's a non-trivial class. So therefore, that's why it's a class and it's non-trivial. On the other hand, in string theory, in type 2b, we know how we can have something whose boundary is a circle. Namely, you can, for example, take F theory, compactified on a hemisphere. And this is viewing F theory as non-perturbative part of type 2b. This will give you a space whose boundary is S1 with a periodic boundary condition. So what happened? Well, what happened was that the characterization here of spin structure was not quite right. In the context of string theory, we can allow spin C structure, and the spin C structure is taking into account that the coupling constant of type 2b could vary. Or equivalently, another way of thinking about it is in the perturbative type 2b setup, you can have a space whose boundary is a circle by using an orientifold. So you can undo the circle by considering the type 2b orientifold. So either way, you can get rid of that class. In other words, the spin manifolds was ignoring the existence of possibility of orientifold singularities, which had been ignored. And if you include that, S1 with a periodic boundary condition becomes trivial. And similarly for this one in the lower dimension. How about, let's say, in dimension 4? What about the K3 case? So in that case, we are now in dimension 4, and you can define the conserved current, which is that global charge, by Pontryagin class. So you define a D-4 form, which is the dual of the Pontryagin class, which is proportional to the dual of R with R. So this is conserved, namely D star J is 0 by triviality, because D of trace of R with R is 0. And therefore, it defines the D-5 form U1 symmetry, global symmetry. And this is normalized for K3 so that the K3 has charge -1. So K3 is the generator of this cobordism class, and it seems like a type 2b has this class. non-trivial class, but it's a global charge. You can measure the Pontryagin class, but that somehow should have a possibility of a source. In fact, we can argue, think of it this way, that there must be a way to be able to get rid of this class. So you can think about throwing the K3 into a black hole. So think about it this way. K3 is a 4-dimensional manifold. So think about this 4-dimensional manifold here. Excise a small region near a point. So this boundary of this is S3, and glue it to the rest of this space, which is R4, through this boundary. So in other words, you can think about this K3 over here as a defect in 4 dimensions. And you can throw it to a black hole, or if you wish, a black brane, depending on the dimensionality we're interested in. And this K3 will fall into this, and that global charge should disappear if the black hole evaporates. And therefore, the K3 class, which has no gauge degree of freedom emanating, there's no remnant of it coming from the black hole, should not be a conserved quantity. So indirectly, we know, therefore, there is this process which can be trivializing this class, this K3 class. But of course, it would be nice to have a simpler description of how the K3 gets trivialized. And we know that it has to be possible from this picture for the lack of global symmetries. Similarly, we can extend this to other cases. For example, we can study M theory. In this case, we study pin plus cobordisms. And if you look at the pin plus cobordism in various dimensions, you get the classes that I have written here. So we have in dimension 0, you have a Z2. In dimension 4, there's this Z16 class. On dimension 8, there are these Z2 and Z32 classes. It turns out that the classes, this one, the Z2 one, and the Z16 class and the Z2 class here are all killed. Sorry, this Z32 class, the RP8 class, are all killed by the M theory orientifold. And what does that mean? Well, in the case of the 0-dimensional one, this is nothing but the Hojava-Witten wall, namely R1 mod Z2. So indeed, this is an example where a quantum gravity does admit a domain wall named the M theory. And indeed, it's a supersymmetric boundary, and it gives you the usual domain wall that has been studied by the Hojava-Witten construction. But the 4 and 8 cases are also have been studied. These correspond to orientifolds in 5, M5 and M9, which gives you these other classes, the RP8 and RP4 and point. So these are trivialized once we take into account that there is orientifolds in M theory. Of course, once we do that, we have to modify the cobordism class we are looking for to allow this kind of orientifold in the characterization, and then start calculating the cobordism again. Of course, when we do that, you get new classes, and then you have to see whether those classes are killed, and then, so this will continue as much as possible until you convert, presumably, to the trivial class. So in other words, once you understand how everything is killed, then you're done. There's a point here that would be interesting to spend a little to explain here. You might ask, how about some of the other classes? For example, this class Z2 here is quaternionic projective space. And this one, turns out that this one is inconsistent for M theory compactification without flux. So if you don't have it, and here I'm talking about cobordism classes without flux. So without flux, this is actually not allowed because it gives rise to a source of G wedge G. There's a source that can potentially have been canceled by G wedge G, but now we are not allowing it, so this is not allowed. So it's anomalous, in other words. So this is illustrating the possibilities that could happen, namely, some cobordism classes could be trivialized by objects. Other ones are actually not there because they're anomalous for other reasons that we haven't taken into account. And this is the case for this one. Now, there are still some other classes left. For example, here in dimension 2, this KB denotes Klein bottle, and in dimension 3, Klein bottle times a circle that hasn't been killed off. In fact, we also, in the case of type 2b, we also had some classes which were not killed off. For example, this point means, what does this 0-dimensional one mean? How would you kill a point in 0 dimension? It means that you have to have a boundary, a space whose boundary is a point, which means that you need to have in type 2b language, the type 2b should admit a boundary. Now, this might sound a bit strange, because how could you have, in a chiral theory, a boundary? And that's what this is predicting. We have to be able to trivialize this, means that the type to be in 10 dimension must admit a boundary. Indeed, there is no contradiction with having a chiral theory, having a boundary. For example, just to give you an example, you can take the usual two-dimensional worksheet and you can admit a boundary like D-branes. And the theory, you might say, is non-chiral when you can do that, but that's not necessarily so, because you can turn on, for example, B field on the worksheet. And if you turn on a B field, then this theory is non-chiral. The theory becomes a chiral because left and right movers are not the same anymore. But still, you know that even if you have B field, you can have modified Dirichlet-Neumann mixed boundaries. So you do admit a boundary for the worksheet. So in other words, chirality is no obstruction to having a boundary. And nevertheless, it would be interesting to see exactly what are these classes, how are these classes killed off. For example, this 0 and this class 4 that I talked about before, the K3 class and the zero-dimensional one. And in fact, we have found that for all the cases that we have studied for the cobordisms, that whenever we get a non-trivial cobordism class, which could be potentially be trivialized by supersymmetric defects, just like some of the examples I was mentioning. So whenever you can find the corresponding supersymmetric object, which you can use to kill it, indeed, there are such supersymmetric objects. And the only ones we have not been able to explicitly construct are the defects which we can show must necessarily be non-supersymmetric. So for example, for the type to be in 10 dimension, for it to have a boundary, it's easy to show that such a boundary will break all supersymmetries. So therefore, we would not have seen it as a supersymmetric object. And this is reassuring because the supersymmetric cases, we have a much better theoretical understanding. So therefore, there is a nice way to be confident. At least the only cases that we have not explicitly identified are the cases that we do not have much understanding about the string dynamics, namely non-supersymmetric case. But that's actually a happy moment because we can turn it around and say that we are learning something about non-supersymmetric sector of string theory. That is, the trivialization of cobordism classes leads to predictions of yet to be constructed non-supersymmetric defects. And this is quite novel because it is giving you a connection between topology and non-supersymmetric aspects of the theory in a quantum gravity theory, which somewhat parallels this similar story going on in the quantum field theory context, where non-triviality of non-trivial topological arguments like higher form symmetries and this and that has led to insights into understanding non-supersymmetric dynamics in quantum field theories in low dimensions. So this is in some sense a parallel of that for quantum gravity. Now, triviality of cobordism classes in particular means that any two quantum gravity backgrounds, say in 3+1 dimensions, can be connected with finite action. There are no superselection rules in quantum gravity. This is quite exciting because it means that any consistent compactification of string theory should be realizable as a bubble in our universe, in the current universe, regardless of precisely what is our universe, regardless of how we obtain our 3+1 dimensional background from string theory. There must be a way to go to any of your favorite compactifications of string theory. If you're interested in compactification, let's say of a type 2B string on Calabi-Yau threefold of the Z manifold, there must be a way to form a bubble of that type in our universe with finite action. So therefore, there's no obstruction in trying to create this. And therefore, this is quite amazing that there's this prediction there. So in particular, of course, it doesn't mean that this object is not hidden behind the horizon of something of some sort. So you could create it, but it may not be. It might be like a black hole. So it might very well be hidden behind the horizon. But at least it's this connectivity of any background in quantum gravity with respect to any other that would be interesting to. That's an interesting prediction of this picture. So. Let me move on to the second topic, which is the topic about the connection between baby universes and the swampland. So closely connected to what we just discussed is the notion of baby universes and what is the story with baby universes and the uniqueness of quantum gravity. So this has been studied a while back, and in particular by Coleman, who pointed out that baby universes, which naively you might have thought that baby universes lead to loss of information. If you if you have some universe here and some degrees of freedom flow out, you may or may not get the information coming to you in your theory, and you might get to think that this is a way that you lose unitarity. And Coleman argued that this is indeed not the case, and if you take into account all the baby universe creation and annihilation through these operators A and A dagger, the net effect of all this baby universe creation and annihilation is basically adding a term in the Lagrangian, where these are A dagger and A can be viewed as operators, or you could go, if you experiment them, do some measurement on them, you can go to their eigenstates after a while, which corresponds to parameters in the Lagrangian. So basically, Coleman's view was the effect of baby universe is nothing but choosing a particular parameters in your Lagrangian. And once you choose these alphas, this will serve as a super selection sector. That means a different L with a different quantum theory with a given alpha, and one with a different alpha are not talking to each other. They're completely independent. And you'll be fine with a situation like that. However, this poses a problem. Since alphas are super selection sector, that means you cannot deform a quantum gravity with alpha to alpha prime if they're not equal. And this is contrary to the evidence we just presented that any quantum gravity should go to any other. So in this case, if you had these alpha parameters, you could not go from one to the other. So that would be a contradiction with this uniqueness I was talking about in the context of Cobordism. So this uniqueness links this story of Cobordism to this story of this baby universes. So the overarching principle seems to be the uniqueness of quantum gravity, which would say something should be wrong with this picture, or something should not be allowed, or in some sense there should be only unique alpha possible, which doesn't correspond to the free parameters in the theory, like the one that Coleman would have talked about. So how do we motivate that this should not be possible? What goes wrong? Well, so if you think about adding a term in the Lagrangian, you can always view the dual of that term in the Lagrangian as a kind of a -1 form current, a -1 form symmetry current defined in this way, which trivially satisfies D star J is 0. And so this suggests that one way of saying is that ability to add these kind of terms to the action should not be allowed. In other words, we should not only rule out 0 form symmetries, we should also, in order to exclude these alpha I vacua, we should also forbid the -1 form symmetry as well. In other words, once we do that, we would effectively say we should not have any of these parameters as free degrees of freedom in our theory. Now, you might ask, do we have any further evidence that maybe we do have parameters like that in string theory? This is not so. In fact, one of the hallmarks of string theory is that all parameters appearing in the action are vacuum expectation value for dynamical fields. There is no free parameter in string theory. There could be sometimes even discrete parameters like fluxes and so on, which could be serving like Chern-Simon levels and so on in the quantum field theories, but they're always dynamical. You can jump them by processes with finite action. Whereas you cannot change alpha from one alpha to another if they are parameters with any finite action. Therefore, it's very different. So having these alphas is contrary to all we know about string theory, which does not admit any free parameters. So it should not be possible. Therefore, we make the following conjecture. This is what we call the baby universe hypothesis. And the conjecture is that in quantum gravitational system with dimension bigger than 3, the dimension of the Hilbert space is equal to 1. The baby universe Hilbert space being one-dimensional excludes all these possible values of alpha except for one unique choice, which we can then identify with the Hartel-Hawking wave function. The restriction to dimension bigger than 3 that we have put in this context is due to the usual restrictions of Swampland conditions, which applies typically to theories of gravity in higher dimensions. So let me elaborate further on that. So, for example, in 2 dimensions, we can have global symmetries. And in the quantum gravity theory, for example, the worksheet of string theories does admit current algebra, which are global symmetries, and there's no problem with the 2D quantum gravity having that. So, morally, the statements that appear in Swampland arise from considerations deeply connected to black holes and unitarity. So these conditions only arise in dimensions bigger than 2. Dimension 3 is a kind of borderline with the gravity is kind of a little trivial. So it's just to be on the safe side, I'm putting here d bigger than 3. But let me say that I believe this. We believe the statement is true for any d, including 2, for the backgrounds which come from string theory itself. In other words, there are no backgrounds from string theory which are like the worksheet itself. In other words, when you compactify string theory, this applies to any dimensions. But just to be on the safe side, I think it would be good to restrict to that, because otherwise we can have like a topological counterexamples, like the string worksheet would be a counterexample to lack of global symmetries in a quantum theory of gravity. And similarly, this is the case here. So in particular, in 2 dimensions, we could have the dimension of a baby universe being bigger than 1, because you could have currents. Now, to say that the dimension of the baby universe Hilbert space is 1-dimensional is strange, because you have a space, you can have all these degrees of freedom. So how could it end up being just 1-dimensional? You have a compact space, you want to put a Hilbert space, you might still think there's a huge number of degrees of freedom. This is somewhat analogous to saying that, I have a compact space, I want to put charges on it. What is it? How many charges, how many possible charges I can put on it? Well, if you have a gate charge, the answer is that you cannot put any net gate charge, so it's 0 on a compact space. Of course, non-compact you can put, but in a compact space you cannot. And the expectation is that the same thing is true here, that the Hilbert space of the baby universe is 1-dimensional in the same sense of neutrality that is part of the Gauss's law for gauge fields. And that the baby universe Hilbert space can be much smaller than would naively be expected has actually been discussed in the literature, and in particular in recent work of Maroff and Maxfield, where it's motivated by other discussions by Jafferys in particular, and Harlow and others. So there's some mechanisms where you can actually get rid of some of the redundancy of the degrees of freedom. There's some equivalences, and in their toy model, they show that in 2 dimensions that they studied, you can cut the dimension of the baby universe Hilbert space. In their examples, it didn't cut it to 1 dimension, but the point was here that you could, in principle, get a much smaller space than naively expected. So one consequence of the conjecture for this hypothesis for the baby universe Hilbert space being one-dimensional is that there is no zero-form global symmetries. In fact, this baby universe hypothesis will, as a consequence, imply that there are no zero-form global symmetries. And the reason for that is that if there were global symmetries, we can consider a baby universe which carries that charge. We just put one of the particular charges in one of the states, and therefore that would be a different state in the baby universe because they're characterized by a different charge, and therefore the baby universe Hilbert space cannot be 1-dimensional. So the 1-dimensionality of the baby universe Hilbert space in particular implies that there are no zero-form global symmetries. And in particular implies, because there are no zero-form global symmetries, similarly that all the gauge particles have a complete spectrum, et cetera, et cetera. So this fits very beautifully with the other principles of the Swampland and implies many of the other ones. So, however, there is actually an argument against the baby universe hypothesis, and that's a point I want to come to, which is related to the ensemble interpretation of ADS-CFT. Some 2-dimensional models require the analog of many baby universe states, and this is related to the ensemble interpretation of ADS-CFT in 2D. So let me try to elaborate that further. Suppose we have these vacuum, the alpha i's that I was talking about, discussed by Coleman, and suppose there's not a unique one. Suppose you have a number of them, not just a Hartrell-Hawking one, and consider a state which is in some particular superposition of these alpha states. Then we can consider an operator corresponding to having an asymptotic boundary in the space X. So view this as some kind of an operator, and computing the expectation value of this in particular state will give you a sum over the expectation value of z's from between the alphas. Now notice that you cannot go by any local operators according to what Coleman has from any alpha to any other alpha. So this would be diagonal, each one of these z-hat operators in a given alpha basis. So this basically becomes the sum of zi squareds for z alpha I. So so you can think about this as a kind of an ensemble, therefore. You can think about this partition function, z of x, as being summed over the partitions for different alpha universes with probabilities given by the coefficients that we have picked for this state. So, so this leads to, if you are doing, for example, in the context of holography, if each x would corresponding to a particular CFD of some kind, you can have, which characterized by some parameter alpha, you can consider an ensemble of them, and you can average over them with some probability distribution and getting a new partition function in the context of this particular wave function for the baby universe. So therefore, the ensemble interpretation of the holography in that context, summing over these kind of partition functions, is natural in the context of having baby universes, which is not unique. Of course, if there's a unique one, if the P is 1 only for one alpha and 0 everywhere else, if there's no other choice, then this would not arise. And this would have given us the regular notion of holography. So having an ensemble interpretation of holography of ADS-CFT is equivalent to allowing for higher dimension for baby universe Hilbert space. Indeed, there are examples of 2D/1D ADS-CFT holography which uses an ensemble picture. And the famous example of this is in the work of Saad, Schenker, and Stanford, where they argue that the JT gravity and matrix model are holographically dual in the sense of this ensemble. Namely, an ensemble of matrix models, namely the integration over the random matrices of suitable type, will give rise to JT gravity. The basic structure in this kind of thing, a more general version of that, would be that you have K quantum systems in one dimension. If, let's say, they are defined by n Hamiltonians, n-dimensional Hilbert space, each one of them, and you have some Hilbert, for each one of these, let's think about each one of them as a collection of circles independently of each other. You have some Hilbert Hamiltonian, which depends on which one we are talking about, and depends on some ensemble, which I call A. So for each choice of an ensemble parameter A, you get some particular Hamiltonian. And you can compute, you can consider the unitary evolution with that Hamiltonian as e to the minus I tau I hi. So this would be the unitary evolution operator. And so you can consider the trace of this evolution operator. So that would be the partition function for each one of those universe circles. But you have an ensemble, so you have to integrate over the ensemble with some measure. So let me define the measure as e to the minus SA integrated over A. And this will be the ensemble interpretation of this bunch of these one-dimensional systems. And the statement that in the context of Saad and Schenker and Stanford would be a system like this ends up having a holographic interpretation in 2 dimensions. And this is this 1D system turns out to be dual to 2D gravity, where the relevant gravity geometry involves a sum over Riemann surfaces with K boundaries. Based on this example, one might think that this is also the case in higher dimensional examples of holography, despite the fact that the ensemble interpretation seems not to be needed in the known higher dimensional examples of holography. So for example, in ADS 5 times 5, we are perfectly fine without any ensemble of summing over different n equals to 4 Yang-Mills. So we are perfect, everything works beautifully. So, but one might think that this should somehow be modified if this is the correct picture. So we have 2 alternatives. Either the higher dimensional examples also require an ensemble interpretation, in which case the baby universe hypothesis is incorrect, because we had said that the baby universe hypothesis in dimensions bigger than 3 should hold, and therefore in these higher dimensions, it should hold. Or the higher dimensional examples work differently from the 2D case. The second alternative is similar to what we have seen in the other examples of exceptions for swampland conditions, for example, like the global symmetry. So the second option, that the higher dimensional examples work differently from the 2D case, that the 2D case is misleading us, is what we want to argue for, and that's what I'm going to discuss now. So now I provide evidence that the higher dimensional version of holography do not involve an ensemble interpretation, and that will be consistent with the baby universe hypothesis. So in fact, I want to argue that the ensemble interpretation, the 1D case, the one I told you about, in this case, we can consider specific case, and not necessarily the case that was in the example that I mentioned in the case of JT, but some general, another example. So let me consider another example to tell you, to explain why this is actually such a generic phenomenon. Take K circles in a D-dimensional sphere. So take a D-dimensional sphere and take K circles. They could be some kind of any configurations you want of these circles, and put a background gauge field connection A on the D-dimensional sphere, and identify this unitary operator, which was the evolution operator around the circle, by the path order exponential of IA around the circles that you're interested in. So the unitary operators will be these evolution operators. In other words, the Hamiltonian times tau is identified with the gauge connection along that corresponding circle. Moreover, let the ensemble measure be nothing but F wedge star F for that connection. So you have an ensemble labeled by a gauge connection in a D-dimensional space, and for each connection you pick, you will get an evolution operator around these circles, which is nothing but the Wilson lines, of course, Wilson loop amplitudes. And then we're supposed to integrate over this ensemble, which means nothing but integrating over the gauge field, which is nothing but doing the path integral over gauge fields. So therefore, what we are actually computing is the expectation value of a Wilson line in a higher dimensional theory. Even though we started with a 1D theory, even though we thought we were talking about a 1D theory, we are ending up computing amplitudes in a higher dimensional theory, and the ensemble, which sounded like a black box in the context of 1D, is nothing but the action in this higher dimensional sense. So in other words, in this context, you will get an ensemble interpretation, and it should be viewed as duality between observables and brain amplitudes in a non-ensemble version of holography. Said differently, in the context of if you're trying to compute the Wilson loop amplitudes in an SUN gauge theory, and if you take n to be large, and if you have suitable fermions or whatnot, you would expect there to be a large and dual alloy 't Hooft. And therefore, the Wilson loop amplitudes will be computed through the worksheet of the gluons, and that's the usual picture that we expect for large n. And so therefore, we do expect that you will get, in principle, the analog of the picture we had before, namely a picture involving a Riemann surface with K boundaries. But we don't think about this as a fundamental theory of a 2D gravity. We only think about this as computing some kind of a brain amplitude, in this case, the worksheet amplitude, in a higher dimensional theory. So this is actually underscores that you can always do this in any theory of a quantum theory, that you can always try to do something which looks like an ensemble, but actually what is running the show is nothing but the higher dimensional theory. The higher dimensional theory is where the complete description is, and it would be funny to say that the complete description of the theory is just computing the Wilson lines, and that's it. That's not the full theory. That's a piece of a full theory. So we should view this as a subsystem, as an incomplete description of the full theory. The full theory is the action that we are dealing in this D dimension, and these are just some observables, the Wilson loop observables.
Cumrun, there's a question by Stefano Cremonesi. He's asking, is the general suggestion that in ADS2 CFT1, the CFT1 should always be viewed as a defect CFT?
Sorry, I didn't hear it.
So Stefano is asking, is the general suggestion that in ADS2 CFT1, the CFT1 should always be viewed as a defect CFT?
No, I'm not saying that. All I'm saying here is that the ensemble interpretation should be naturally viewed as belonging to a higher dimensional one. You may have a non-ensemble version of the holography. I'm not talking about that. The ensemble version of it, I'm saying, is. In fact, it turns out exactly the same is true for JT gravity. So in fact, JT gravity, I will now show that it should be viewed as an incomplete theory in the same sense as the Wilson loops should not be viewed as a worksheet theory. It's not a two-dimensional theory. It's just perturbative amplitudes in a higher dimensional theory. And I will now argue that the JT gravity is nothing, it's exactly like that, and should be viewed as worksheet amplitudes in a complete higher dimensional theory of gravity. And in fact, I will argue in a six-dimensional theory of gravity. So how does that work? Well, JT gravity, will be related as worldsheet amplitudes in a 6-dimensional gravitational theory, namely Kodaira-Spencer theory of gravity, which is the gravity description of a topological B model on a Calabi-Yau manifold. Indeed, JT gravity is the worldsheet perturbation amplitudes for topological V model on a Calabi-Yau and a local non-compact Calabi-Yau given by y squared minus sine squared root x plus u squared plus v squared equals 0. If you compute the worldsheet amplitudes in this theory, you get amplitudes of JT gravity, which is dual to the, so indeed, this is the gravity side of it. And the gravity side of it, you might ask, what is the gauge theory side of it? What's the holography side of it? And this is the kind of thing that actually arises in the context of a model very well known in the context of Chern-Simons theory. For example, the conifold, if you have y squared plus x squared plus u squared plus v squared is 0 in the context of type A model topological strings, and you compute, you put branes around them, you get Chern-Simons gauge theory on S3, which is dual to the resolved to the blown up conifold. And that is the holography in that context, which in the B model will give you these kind of objects being dual to matrix models. In fact, as we argued with Dijkgraaf a while back, such a B model, topological B model, is dual to a matrix model exactly of the type that Schenker and collaborators were suggesting, given by the spectral curve, given by y squared is sine squared root x. And this, according to Eynard and Orantan, is equivalent to Mirzakhani's model, which indeed computes the partition functions of JT gravity. So JT gravity arises nothing but in this context from this higher dimensional perspective as a piece of the computation. It is like saying in the context of matrix model, if you take the Gaussian matrix model, you could view the Chern-Simons gauge theory as amplitudes of Chern-Simons gauge theory as being related to a matrix model. Of course, that's not the full theory, that's a piece of the theory. And in the very same sense, JT gravity should be viewed as such. It's a piece of that. And this removes all these extra degrees of freedom of what chooses that ensemble, how are you allowed to do that? It seems like you have infinitely many choices, but from the higher perspective, it's nothing but choosing of a particular 6D geometry and observable. And therefore it's nothing new, and it should be viewed in the same regular form that we are familiar with. So this underscores that ensemble interpretation is not the right way of interpreting the holography. It's always embedded in the higher dimensional picture. So nevertheless, you can ask, can there be a higher dimensional ensemble holography? So here we had the 2D holography arising from a 1D system. Can higher versions arise? Based on what we discussed, it's natural to expect that if it were the case, it should be viewed as a branes in a higher dimensional gravity theory. And the only such cases that we know, the highest you can go is M2 branes in terms of the holographic dual objects that could be describing. For example, if you have a holography involving M5 branes in 6 dimensions, we know the corresponding analog of the observables in that case are M2 branes. So you might imagine that there is an exception similar to what you had between 1 and 2. It could be between 2 and 3. You can have two-form observables, two-cycle observables in the theory of M5 branes, which could be dual to a 3-dimensional gravity theory in the similar sense. So there could be an exception in 3 dimensions, but even so, even if there is, the language would be clearly suggest that this is not the fundamental description of the theory, and the correct description should be viewed as some theory, as viewed in a higher dimensional theory, namely, in this case, coming from in that case, it would be ADS7, let's say, for S times S4, rather than the corresponding object that it gave rise to. So therefore, this shows that the baby universe hypothesis actually sheds light, and it's actually connected with the fact that you cannot push one should not expect to push this ensemble interpretation to too high a dimension. And this is consistent beautifully with the fact that the Swampland conditions typically are different between low and higher dimensions. And this fits beautifully with this hypothesis. So I think that's where I want to stop, and I will open up for questions. Thank you.
Okay, great. Thanks for the great talk. Questions from the audience? Looks like Nadi has a question. Or is he just clapping?
Yeah, I'm here. I hope you can hear me.
Yes.
Yes, I can hear.
Good. I'm not sure it's directly, but certainly indirectly related to your talk. if you start in ordinary string theory and you compactify it, say, on a torus down to two non-compact dimensions, then the dilaton is a number, it's not a field. How does this fit your picture? Could I explain why I say that it's a number and not a field? Or is that, I think you know that.
Well, what do you mean by number, not a field?
So if you count the number of degrees of freedom in fields, in gravity and dilaton, and d mu nu, and you substitute d equals 2, you get 0. And one way to think about it is that there are various ways of thinking about it. There's no b mu nu, and the metric is -1 degree of freedom, which eats the dilaton, and you're left with just 0 mode of the dilaton, which is not.
Sorry, Nati, are you talking about 2D string theory, or you're talking about compactification to 2D? There are two different things.
Well,
because
I'm not thinking about C equals 1. I'm not thinking about C.
2D string theory is different from this, and I can explain why.
Yeah, I'm actually not thinking about C equals 1. Where,
you're not thinking about that? Then I'm not sure what you mean by the dilaton is dynamical still. You can change the values.
No, you can only change the geometry. You lose 1 degree.
Well, the geometry is not, you cannot freeze the geometry, of course. You cannot freeze the geometry. So the compactification.
So imagine you compactify on something that doesn't have moduli or whatever.
No. I'm just saying that's exactly the point. Exactly the point is that every quantum gravity will be connected and you cannot stop it. There's no asymptotic condition in 2D that freezes it.
Well, at least in the bosonic string, there are examples with no moduli.
It doesn't matter. All I'm saying is that you cannot freeze the geometry. In other words, the uniqueness of quantum gravity backgrounds exactly says you cannot do what you're saying.
Okay. Thank you.
Cool.
More questions? Okay. I have a question. So you were talking about the non-supersymmetric defects. So these are supposed to be stable objects or not stable?
Good question. In some sense, they should be stable in the sense that they are replacing a Cobordism class. So in some sense, they should have a meaning to them. Yes, I expect them to be in some sense stable.
Okay, so it wouldn't be like a conventional object, like say a D8 brane in 2B or something like that.
Well, it should be. It's a non-supersymmetric stable object. Yeah. Somewhat like spin. In the case of heterotic string, you can have stable higher spin, like in spin 32 state.
I see. Okay. Anything else?
Would it be dynamical or more like an orientable?
Sorry, they would be object. Every object is in some sense dynamic. We don't have, well, it depends on what you mean by dynamical, but they could be like orientables is a defect. So it could be in the same sense.
Yeah, that's what I meant.
Yes.
Yeah. Mm-hmm. Okay, any other questions?
I had a question about the ensemble interpretation and the ADS2 holography. There was a question whether all the ADS2 holography due to CFT1s has to be done by the theories have to be boundaries. Actually, if one can actually do ADS2 CFT1 holography very easily once you realize that the CFT1 ground states don't preserve conformal invariance. And then all the CFT1 ground states are just dual to an ADS2, which has an infrared cap. This is not JT gravity. JT gravity is not in this category. But for example, in string theory, there are many examples of solutions which are asymptotically ADS2 with a cap. And there, the theory is very happy. It's not it's just a nice vanilla holography. So I think the main issue is JT gravity, using it as a toy model for ADS2 holography. But ADS2 holography in itself is actually nice and happy.
Yeah, I didn't have any comments about ADS2 CFT1 holography per se. I was just interpreting the ensemble as viewing as coming from higher dimensions. So in some sense, it's natural to expect ensemble is an incomplete description. Like if you start with an ensemble, why did you choose that ensemble? What about a different ensemble? It's incomplete. And in some sense, it is like the same thing as choosing a particular observable in a higher dimensional theory, which is also incomplete. You can choose many different observables. So the name of the game is the higher dimensional theory, not the ensemble itself.
Mm-hmm.
Okay, more questions.
Joe Minahan has a raised hand.
Hi,
okay.
Yeah, so it's the best that I know, Cobordisms only go between manifolds of the same dimension.
Yes.
But string theories, of course, live in different dimensions. Is there
Yeah.
some way to generalize this to like going between different dimensions or anything?
Good
like
question. Good question. I wish I knew how to do it. Of course, string theory suggests that there should be a way to describe it because we have a physical process to go from one to the other. But there's no mathematical formalism that, you know, if we had a good answer to your question, we would be in good shape in understanding string theory geometry better. But when I was talking about cobordism, I meant in the more general sense that you were just talking about, and not just fixing a particular background.
Okay, thank you.
Well,
Other questions? Be polite. You can just shout it out if you want.
Hey, I have a question. Thank you for the great talk. Are you saying that not having an ensemble interpretation in higher dimensional holography necessarily implies that your baby universe hypothesis is true?
no, I
Or
went the other way. I went the other way. I said that if the baby universe hypothesis is true, then you're going to have trouble with the higher, you will have trouble with the ensemble interpretation, not the other way around.
okay, thanks.
I mean, the other way around should be true as well, though, right? If you don't have an ensemble average, then just the axioms of local quantum field theory for the conformal field theory say that the Hilbert space, if you quantize it on the empty manifold, is one-dimensional. So in some sense, it should go back the other way as well.
By the way, Jake is my student, who's my collaborator, is just responding.
Okay, other questions? Best chance?
Can I ask?
Okay. Yes,
Sorry.
please.
Yes. So if I look at multi-trace deformations where we have again some over different couplings, so you can view it as an ensemble. So that will fit in your picture, right? You will say that this is standard holography with different boundary conditions.
Yes, exactly.
Okay, anything else? See anything? So let's thank Cumrun again.
Thank you. Thanks for listening, everybody.
Yeah.
And keep safe.
Yeah. Okay, and we'll have the next talk in 2 weeks. So stay tuned for that. Bye-bye. Thanks.
Thank you. Bye-bye.
Thanks.
Thank you.
Thank you, everyone.
Yes.